will keep telling us more about Positroids.
All right, so let's see. So we were talking about realizability. That was the last thing I said. And this basically for your flag of matroids, you should have alongside it this flag of subspaces, these vector subspaces, where each subspace should basically identify with its corresponding matroid. An example of such a flag matroid would be the uniform matroid. So you can play this game by considering this particular matrix representation for the uniform matroid. And basically you just start chopping off rows from the bottom. And as you do that, you're immediately, you recognize there's a vector space associated to this, as well as this matrix represents the associated uniform matroid. So you sort of, in both hands, you've got the flag of uniform matroids and the flag of the vector spaces. And this one's particularly nice because this truncation on this matrix is super simple. So you actually have one matrix that basically kind of encodes everything that you want, which is sort of the ideal situation. Okay, so to get onto this topic of quotients, I'd said there's this definition of flags that's important to know, but it's definitely not the definition that we use moving forward. And the reason is because Borovic, Gelfand, and White said that a set of flags forms a flag matroid if and only if the following holds, which is that every constituent is a matroid, and this just means like pairs. So constituents are just the matroids themselves in your flag, and that all pairs of these matroids or these constituents form a quotient. And I'll define what a quotient is in a second. And every appropriate flag of bases is a flag. Okay, but so really the quotient is the most important thing here. So this theorem tells us that to understand quotients is enough to understand the flags. And so we really then said, okay, if we want to make some progress on this question, why don't we just start by saying, how can we combinatorially characterize these quotients of positroids? So what is a quotient? A quotient is, let's take two matroids over the same ground set, and one matroid has rank less than the other. So we'll say M has rank less than N. Then M is a quotient of N if every circuit of the larger rank matroid of matroid N is just a union of circuits of the lower rank matroid. So here we've got really this is the uniform matroid. Is that true? Wait, no. I take that back. We just have a matroid of rank 3. Its only circuit is, wait, hold on a second. Now I've confused myself with my example here. So its circuit is 1, 3, 4. Yeah. Okay, apologize. So we've got our matroid with the circuit 1, 3, 4. And then we have the lower rank matroid where the circuits are 4 and 1, 3. And you can see that if I take the union of the circuits 4 and 1, 3, I get exactly the circuit 1, 3, 4. And so then I can say that M is a quotient of N. And so how can we try to capture this idea of quotients in terms of these decorated permutations, of these special permutations that represent the positroid? Okay, so one interesting thing that we noticed here is that because the ranks, right, the rank kind of already gives a natural ordering to the matroids that we're interested in, or the positroids, that we can actually then say, well, why don't we just generate a post set of positroids ranked in such a way that their one positroid is less than another positroid if they form a quotient. And so then that gives us the following post set of positroid quotients, which to our knowledge is something new. There's definitely work out there that has looked at this type of post set for matroids, but I don't think anything so extensive, other than just that you could create such a thing, but it doesn't seem like there's much work out there that explores these type of post set in this way. Um, so essentially, you're just taking all the, I mean, the way that we're looking at it here is taking all the decorated permutations for your positroids and then order them depending on if they form a quotient. And the ones that I've highlighted in red here are actually the decorated permutations that represent the uniform positroids. So I actually skipped ahead of myself. One thing I didn't mention is that uniform matroids are positroids. And so we naturally have this very nice matroid at our disposal. And you can see here, like if I have bars above all of my values, that means each one of these 1, 2, and 3 must be in a basis. And since my ground set is exactly all the values you see there, 1, 2, 3, then that means the only basis in the positroid represented by this decorated permutation is the basis 1, 2, 3. So that is the uniform matroid of rank 3 over the ground set 1, 2, 3. And then we just kind of follow our way down. Uniform matroid of rank 2 over 3 elements, uniform matroid of rank 1, and then uniform matroid of rank 0. And I'm going to be loose here because I really should say decorated permutation representing the positroid, but that's a mouthful. But each one of these really is like a positroid behind the scenes. Cool. Okay, so what I want to just mention are a few of these important facts for uniform positroids. One is that these uniform matroids are positroids. Another one is that their Grassmann necklaces are really nice because if I want to say consider rank 3 over the ground set 5, I know that all of the bases are just the triplets, any subset of rank 3. So then I know exactly what these elements look like without having to do any of this Igale order comparison stuff. The decorated permutation ends up looking really nice. There's a way you can write it in terms of, N and K, but really an example I think says a lot here. So if I have rank 3 over 5 elements, I start with my rank. So I'm taking n minus k plus 1, but here it ends up being the rank 3. And then I just add 1 until I get to the total ground set value. And then I just start over. And this is how all these decorated permutations look. So it's really nice. And then the circuits are also really nice. So if I consider the rank 3 over ground set 5 uniform positroid, then all the circuits are just all the subsets of size 4. Okay, so these are just like nice properties that we want to keep in mind as we move ahead. Now, one thing that we did when we saw this information, which I guarantee anybody looking at this would find it eventually, is that we noticed, let me back up here, we noticed that if we started at a decorated permutation, and I said, let me just fix some subset of these numbers, like, let me find something easy. Let's see, if we fix 2, and then all the other values, I'm just going to cyclically shift to the left. And if I get to a place where I don't have room to move the next number, I'm just going to circle back around and stick it on the end, whatever the first open spot is that I can put it in. So like I fix 2, and then I shift everything over to the left. So 4 should go next, then 1, and then 3 just replaces 1. So that's 2, 4, 1, 3. And do we see it? 2, 4, 1, 3 is right here. That means I can basically play this game where I say, let's pick a subset, let's fix it. I'm going to cyclically shift everything else 1 position to the left. And if I happen to form a fixed value in that process, I'm just going to label it with a bar below. And I'll do another example in a second. So we called this I think I actually called it the decorate, but this is an older slide. I apologize, I didn't update it. Free shift color function or free shift decorate function. And it's exactly what I just said, where we take some subset of our ground set for a decorated permutation. We'll freeze all the values in that subset. we will cyclically shift everything else one position to the left, jumping over a frozen set if we have to, and then, attaching it to cyclically around to the next open spot. And if we happen to fix anything, we'll color it with a bar below. Okay, so we introduced this function on these decorated permutations. And here's that one we just did, fix 2, cyclically shift the rest of the elements. We could also say, what if we were to fix 2 and 1? So we fixed positions or values 2 and 1. That just swaps 3 and 4, which gives us this permutation here. And since we fixed 3 in that process, we color it with the bar below. And each one of these decorative permutations you can generate by applying this free shift color function. So that's one of the first results that we have. I apologize that this is so wordy, but essentially the first thing is, the goal is to really try to describe these quotients. So we need to make sure the ranks work. So this first theorem is really just saying, once you apply this free shift decorate or free shift color function, you actually drop rank by 1. So you've gone from one decorated permutation to a new one. And it really means that you've got a positroid that you started with, and now you've just generated a new positroid that's rank 1 less, which is good because now you have 2 candidates that might form a quotient. Okay, and this is just sort of a simple way of saying that when you take a certain size of a fixed size that's less than the rank of your positroids, then you drop by rank k minus 1. Okay. Then we also remember quotients were like we have differing ranks, and then we also have that the union of the circuits of the larger rank is a union, that the circuit of the larger rank positroid is a union of the circuits of the lower rank. So we also need to say something about the circuits of these 2 positroids that we're playing around with. So this first statement here is essentially explaining how we can write these circuits dependent on this fixed subset that we've chosen. And it looks a little complicated here, but the takeaway is that if you know the positions that you've fixed, then that actually leads you to knowing an interval that you can use to describe the circuits of the positroid. And then any other subset of the right size that doesn't contain this new interval that you've just found is also a circuit. That's what this whole theorem is saying, but let's look at an example because that'll definitely help clear this up. So this remark is just what I basically said, is that the circuits can really be read just by looking at the decorated permutations and the frozen sets that you've chosen. Okay, so for example, if we start with this decorated permutation here, so what this really is the decorated permutation for the uniform matroid of rank 7 over 13 elements. So you can see it has this same setup where we start with the rank 7, we go up 8, 9, 10, 11, 12, 13, and then just start over 1, 2, 3, 4, 5, 6. That was one of those properties of the uniform positroid that I pointed out earlier. Now we want to fix the subset 12. Now this interval, I'm going to read it as just a cyclic interval. So this says I actually want 12, 13, 1, and 2. That's the set I've fixed here. And then I'm also going to fix the set 4, 5. And I've just highlighted them in red here on the permutation, so you can see those easily. So those are the values of the permutation we fix. Everything else, we cyclically shift 1 position over. And if we fixed anything right, we color it. In this case, we didn't do that. But here's the cool thing. Oh, sorry. I think it's cool. You can guess this out. You can let me know if you agree. So we've, this thing's getting in the way here, isn't it? You can't see this here. Okay. Let me see if I can just do this instead. Oh, is that going to help? Yes. Okay, great. So we fixed this set that means I'm going to look to its left, and I see that it gives me basically an interval here where I read this as the value in the position 3 to the position 5. So this gives me an interval 3 to 5. And it's going to be the cyclic interval again, but in this case, it doesn't matter. It's just 3, 4, 5. That is one of the circuits. Here's my other fixed set. I look to its left and I see 6 to 10, which gives me the other circuit, which is the values 6, 7, 8, 9, and 10. So these two intervals, which I could immediately read from the decorated permutation, are two of the circuits that are maybe a bit strange, but then all the other circuits, because I started with this uniform matroid, I meant to update this and I keep forgetting. I started with a uniform matroid of rank 7. So really I should be considering all matroids of rank 6, all subsets of size 6 here that would generate the rest of the circuits. I apologize, this 5 should be a 6. This is super annoying because I've done this before and I keep forgetting to update my slide. So let me back up because I'm saying this wrong. So we started with the uniform matroid of rank 7. When we get to our new positroid, it has rank 6, one less. So that means any circuit that I'm considering here, I could think about it as if it was uniform, should have rank 7. And that means the rest of the circuits in this set should have rank 7, except for these two weird ones that I picked up. And so any other circuit, as long as they don't contain these two and have the right rank, those are the rest of the circuits. Okay, but really the take home here is that these fixed sets point to us these other circuits that we otherwise, wouldn't be able to catch. Okay, I think I'm close to time here, so let me just kind of wrap this up. We basically were able to describe the rank that we needed, that the rank changes as we apply this function, and that we at least have a description for the circuits of the new positroid. I won't go into the details, but we did show that the uniform matroid circuits can be formed as unions of the new positroid circuits that we found. So that's clear. And so then we have what we need, which is that this new decorated permutation represents a positroid that does form a quotient with the uniform positroid that we started with. And let me just get to that statement. Okay, I guess that was it. The only drawback here is that this is sort of an if and only if statement up to rank 5. And so once you start looking at higher ranks, 6 and above, our free shift decorate or free shift color function works. You can still generate positroids this way, you just don't get them all. And so here's an example of 2 decorated permutations that you cannot get once you play this game. And it's because the size of the frozen set actually is restricted. And I didn't really make a big deal out of that before, just because I think it's important, but not to like understand what we're doing. But you can't pick a frozen set that's any larger than the rank. And so once you have that restriction, it really means that you're missing out on some of the positroids. But the cool thing that leads us to conjecture maybe there is a version of this that works is that if I look at the decorated permutations of the things that are missing, and I know that I've chosen the right frozen set, even if it's larger than what I say I should have chosen before, this whole process of freezing, shifting, and coloring still works. So there's something we haven't quite sorted out how we can relieve ourselves of this restriction on the frozen set cardinality. But if there's a way to work around that, then I think there should be some version of this free shift color function that allows you to generate all of these positroids that form quotients. And then I'll just end by saying, if you're interested in posets, this positroid quotient, poset of positroid quotients is really interesting. I know Catalina's been working on it with a graduate student. So They have some work pending that should be out soon. And this circuit description that I gave is very specific to this particular case. It's not known if there's like a general circuit description for positroids. So that would also be something that would be fun to look at, is if this might lead you to a more general description for circuits for positroids. And it came to our attention that maybe it was at the beginning of last year, a paper came out by Lukowski, Parisi, and Williams that had basically like this free shift color function, but not as general as ours, used for some work that they've done there, which was really cool. So I think, you know, there's something to this that is shown to be useful. And then I just highlighted a couple other papers here if you're interested in sort of looking along these directions. These are two papers that I would highly recommend that you take a look at. I think that's all I have. Yes, okay. Thanks, everyone.
Thank you, Anastasia. Any questions?
So I have a question about this post. It looks really interesting. The Mobius function. You mentioned the Mobius function. Does it seem like it's nice, or like, or but it seemed like
yeah, when we looked at it before, it did not look nice. And Catalina's probably a good contact if you wanted to follow up with her a little bit to see what they've done with that. I tried to get an update on that, and I wasn't able to do it in time for the talk today. But yeah, I mean, I remember when we were generating some Mobius, just like counting up values for these ranks, like they were not pretty numbers. So I'm not sure what process or what progress has been made there.
Do you have some sense of how many Positroids you're missing from the free shift decorate process as n grows?
Yeah, I know we computed that at some point, and I don't believe there was like I mean, probably the easiest way to compute it would just be to actually, so you can count these positroids basically, well, let me think here. I can never say this name, but Narayama numbers count positroids. And actually, Alejandro, we were talking about this at your talk at UC Berkeley. And after we finished, I went and double checked that that was true. So if that's something that you're interested in, I can talk to you a little bit more about that. But the other thing that one can do, which I hadn't thought about how that affects this, because as you can see, there's a lot of fixed points as we consider these permutations, is that you can also think about decorated permutations without the fixed points. So, which are just arrangements. And I'll step back from that thought, actually. I don't think I've followed that one out too far. But yeah, I know we computed this. I don't think we had a nice formula or anything, but there's that's a computation that wouldn't be too hard to do. Sorry, long-winded answer to your simple question.
More questions for Anastasia?
Yeah, I actually had kind of a similar question about sort of the characterization of positroids, and if there was any way to explain like which ones you were missing in particular, like maybe a kind of decomposition of positroids or something.
Yeah, that's certainly something we were hoping to be able to get a better grasp on. I mean, one thing I can say that's maybe not so enlightening is the stuff that's missing would come from appeared frozen sets that have to be larger, equal to or larger than the rank of the post set. But I can't say for certain if that's enough to say which ones are missing. Like if I took a subset of size K and then tried to play this game, you know, is that always here's the trouble with that is you can always say let's fix a subset and rotate, and then we'll color things. You're going to get another decorated permutation no problem. The only trouble is you may not end up getting something that forms a quotient. And so to get this extra quotient property, that part I don't remember how. Well, okay, to be honest, we didn't come up with any good reason why certain sets work and others don't. Yeah. That would be the goal, right? Is to figure that out. Yeah.
Yeah. Is there any like kind of characterization of positroids, whether or not it aligns with the free shift color function?
Well, I'm not sure if I'm going to answer your question, answer the question you're asking. So what I heard was, I guess, if you take a decorated permutation and you freeze some of it and you rotate and fix things, you're guaranteed to get a new positroid. Is that what you're saying?
Oh, I was more asking if there are ways you could, like, I don't know, categorize like all, I don't know, like some linear algebra properties by which you could.
Yes. Yeah. Thank you. No, this question comes up every time and I haven't been able to figure it out. And I think it's, I don't know, maybe there's a part of me that just thinks it's too hard for me to understand, but yes, that this question, the only thing I can say about it is that positroids are sort of like a generalized, oh my gosh, cyclic polytope. And Alejandro, maybe you have things to say about this better than I do, but when I think about this idea of freezing, shifting, and coloring, I kind of imagine this sort of like twisted, something twisting in space, but I don't know what that looks like. But that's the feeling that I get, and I don't know beyond that. And I haven't had any luck coming across anything that people have written about that, or I've heard that there might be some lectures that Postnikov has that kind of goes into this stuff, but I haven't had any luck finding that. So it's a great question. The geometry of it, I think, needs to be unpacked for sure.
Thank you.
Yeah.
Any more questions?
I mean, I had another one, but I don't want to, like, if other people have questions too.
Go for it, Lizzie.
Yeah, I was wondering about like the definition of a quotient. I don't know, when I encounter the word quotient in other contexts, it's usually like you get a quotient of something by something, but here it's like a quotient is a relationship between like two matroids, and there's not like a quotienting by another thing. I was just wondering like why it's called a quotient, and like, yeah.
I don't have a good answer for that. I'm sorry.
Okay.
It's definitely something that's been on my mind too. And I want to say that it must have something to do with like quotients that we might think of that kind of come from algebra, like an algebraic kind of group theory type quotient, but I don't. That's something that's on my to-do list still, and I haven't come across anything useful for that yet. I keep looking, but it's not there yet. Unless somebody, I don't know if anybody has ideas on that, but you're hitting me with some really good ones.
I don't know.
I'm looking at it and it just kind of makes sense that it would maybe come from algebra, but I've just seen all these definitions because of, well, not all of them, but my internet's been spotty. So I've been missing bits and pieces, but just the fact that the circuits of the quotient are unions of circuits of the bigger matroid kind of makes me think of swallowing as in groups. So
Yeah, I mean, if you like, I don't know if there's a linear like algebra quotient term, but if you like delete the last row of n and then it becomes m, that feels like a quotient-y thing.
Yeah, actually, you know, you're raising a good point, which is something I've kind of hidden here, is that by deleting this row, we're essentially forming a matroid minor. So in this case, yes, that works. in other instances, I mean, I don't have a good example in my back pocket, but there's certainly matroids that we could say form quotients, but I'm not able to. Maybe one could, but I wouldn't be able to come up with two matrices where one is just a truncation of the other. So like I said, I don't know that that's an impossible thing to ask for, but I think this was especially, I created this example special in that way.
All right, if there's no more questions, let's thank Anastasia again for a beautiful talk.